Hello everyone. In today's lecture, I will cover FET biasing. There are three different biasing: fixed biasing, self biasing, and voltage divider biasing. Then I will cover FET as an amplifier and FET as a switch. In detail, I will explain different types of biasing. So, the commonly used techniques for FET biasing are: first one is fixed bias, that is also known as the gate bias circuit. Second one is self bias circuit, voltage divider bias circuit. Before starting the biasing circuit, like BJT, the FET also operate in three different regions. In cutoff region, the application as an open switch. In saturation region, it is as amplifier. In ohmic region, the FET work as a closed switch. The Q point of JFET circuit will have coordinate of VDSQ and ID. The Q points should remain stable in spite of any variation in temperature. The FET is voltage control device due to its special types of construction, and so reverse bias gate source junction, its gate current is very small. So we can write ID approximately 0. So VD equal to ID. ID is equal to IS. So one by one I will explain each region. So first I will start with biasing in ohmic region. When JFET operates in ohmic region, it is equivalent to a resistance. So fixed bias configuration. In the figure you can see the fixed bias region. A negative voltage VGG is applied to gate with a biasing resistance RG. Due to this biasing, the drain current ID, which is less than IDSS, will start flowing. The figure you can see the current will flow. This drain current flow through device. Apply KVL to this drain loop. We get, if we will apply, then our VDD is equal to IDRD plus VDS. VDS is equal to VDD. So VDS is equal to VDD minus IDRD. Here we have applied the Kirchhoff voltage, so VD is equal to VDD minus IDRD. The single subscript voltage refer to voltage at point with respect to ground. So here we can write Vs equal to 0. Using double subscript notations, VDS, if we apply the KVL, this figure, the VDS equal to, that is voltage difference between drain and source, that is VD minus Vs. As we have Vs equal to 0, so VD equal to VDS. Another potential difference, that is VGS equal to VG minus Vs. Here also Vs equal to 0, so Vg equal to VDS. The fixed biasing or gate biasing is a worst why the biasing of FET in the active region, because Q point with this biasing scheme is extremely uncertain. This fact is shown in graphically. Here you can see the Q point. A particular JFET has IDS varying between two different points. Suppose the 4 milliampere or 60 ampere, and VGS of varying from minus 2 volt to minus 8 volt. Thus the ID varies a lot for gate bias circuit. The Q point also will change its positive position accordingly. Therefore this circuit is not suitable for biasing FET in saturation region. For the fixed bias circuit, from this figure you can see the VDS equal to 0, VDD is equal to ID saturation RD, ID saturation VDD by RD. In ohmic region, the JFET equivalent to closed switch, so the resistance is very small. and therefore on state voltage VDS across it will be equal to 0. So it is work as a closed switch. In this region, the JFET work as a closed switch. Another biasing circuit, that is in a saturation region. For that, we have used the self-pass configuration. In this circuit, you can see the self-bias configuration. The self-bias configuration for FET is shown in figure. This configuration need only one DC supply. This is the advantage over fixed bias circuit. Next, DC analysis of self-bias circuit. For DC analysis, capacitance C1 and C2 considered to as an open switch. Here we have applied DC analysis. So capacitor open circuit, RG will be replaced by short circuit. So IG equal to 0. So this is the equivalent DC analysis for self-biasing. So we will obtain different expression. First is VGS. From simplified DC circuit, this is a simplified DC circuit. IS equal to ID. The voltage across RS, this one, is equal to VDS is equal to ISRS is equal to IDRS. Apply KVL to gate circuit. So VGS equal to minus IDRS. Another expression, that is ID. From Schottky equation, that is ID equal to IDSS in bracket 1 minus VGS divided by VP whole square. Now substitute the value of VGS from equation number 1 from this equation. So ID is equal to IDSS 1 plus IDRS divided by VP whole square. To obtain VDS, apply KVL to the drain loop. In this loop, we will apply the KVL. So VDD is equal to ID RD plus VDSQ plus IDRS. This one. If you substitute, if we combine both voltages, so VDSQ equal to VDD minus IDRD, IDQ in bracket RDRS. So this is the DC analysis of self-pass. Current through RS is the source current IS, but IS equal to ID. So from the last equation, VGS equal to minus IDRS. And this we have already discussed. What is the effect that will affect through the RS, that you can see from the graphical representation? Since VGS equal to minus IDRS, this circuit creates its own bias by using voltage developed across RS to reverse basket. Above figure show the effect of different value of RS. These lines are known as a bias line, and the intersect of the bias line with transconductance curve gives the Q point. Here you can see the Q point. For mid value of the RS, if RS equal to RD is gate voltage VGS equal to 1 by 2 VGS off, and ID is equal to 1 by 2 IDSS by 4, and Q point will be in active region, saturation region. The transfer characteristic defined using 4 different techniques. Last techniques, that is biasing in active region. For that, here voltage divider rule is applied. Here you can see the voltage divider biasing circuit. In this circuit, you can see the configuration is exactly same as the one used for biasing transistor. But DC analysis is extremely different. The DC analysis for this circuit is, it will assume that Vg equal to 0, gate current equal to 0. The coupling capacitance C1 and C2 and Cs are assumed to be open circuited for DC analysis. In addition, the source voltage VDD is separated into the two equivalent source. This equivalent circuit you can see in the figure. The simplified voltage divided bias for DC analysis is shown in figure. This is a simplified circuit. So one by one we will obtain different expression. First, obtain the expression for Vg. Vg is the voltage across R2. Vg is the voltage across R2. So Vg equal to R2 VDD divided by R1 plus R2. This is the voltage divider rule. Next one is obtain expression for VGS. Apply KVL to the gate source circuit. This is the gate source circuit. So apply KVL. So it becomes VDD is equal to IDRD plus VDS plus IDRS. So VDS is equal to VDD minus ID in bracket RD plus RS. Similarly, we can expression for the VD. So VD is equal to VDD minus ID RD. The value of ID can obtain by using Schottky equations. We have already ID equal to IDSS 1 minus VGS divided by VP whole square. VDS is equal to VDD minus IDS in bracket RS plus RD. So we can write VDS is equal to VDD minus IDQ RS plus RD. At last expression, that is IDQ. ID is equal to Vs by Rs, but Vs is equal to Vg minus Vgs by Rs. So ID is equal to Vg minus Vgs divided by Rs. If Vg is equal to 0, then it is Vg by Rs. The Vg is large, it can make variation in VGS ineffective from one JFET to the other. So IDQ is almost constant for JFET. In order to bias JFET in saturation region, VDS should be greater than ID RS and less than VDD as shown in figure. So this is the last biasing. Another question asked in GT that does the thermal runaway take place in FET? In FET it doesn't take place. FET has a positive temperature coefficient, that means with increasing temperature resistance is increased. As temperature increase, resistance of FET increase, so current through FET will decrease. So power dissipation will decrease. These reduce the junction temperature. This action prevents thermal runaway. Another application of FET as amplifier. The JFET can be used for amplification of the small time varying signals. The amplification configuration are common source, common emitter, common gate, common drain. Here you can see the figure, common source JFET amplifier. In order to operate JFET as an amplifier, it is necessary to operate in saturation region of its drain characteristic. In above circuit, the N-channel FET being used as amplifier. The fixed bias arrangement is used. The voltage source VGG is used in reverse bias gate to source junction of JFET. C1 is the coupling AC input voltage to the gate of the FET. Isolate DC voltage VGG from AC inputs. C1 is a coupling only AC voltage from the drain terminal. RD is the external resistance with control drain current. This is a common source FET amplifier. Thank you.